Okay, hello everybody. I would like to present you the results of the HiFi Elements project. HiFi Elements means High Fidelity Electric Modeling and Testing. My name is Jens Ebert. I am project coordinator of HiFi Elements and I work for FEV Europe in Aachen, Germany. So HiFi Elements is to improve the battery electric vehicle workflow with its results. It's you found a project with 16 partners in the LCGVO 7 2017 call. It started in October 2017 and runs until the end of this year. So we have partners from all over across Europe. As you can see, we have engineering services providers. We have tier 1 suppliers. We have research institutions from academia, as well as OEMs, mainly here Ford, Iveco Ultra, and Jeep, who are complementing our project here from the OEM side. Our work scope means that we want to develop effort-saving automation methods for calibration and testing and increase the test coverage for battery electric vehicles with our developments. And main topic is the simulation of the whole battery electric vehicle, for which we are proposing a standard for the simulation system architecture. And when you, let's say, subdivide this architecture into components, we also standardize, let's say, what we understand under such a component, and we define the interfaces between the components. Those component models, according to the standard, are being also implemented and developed in HiFi Elements. And then also we have developed a toolchain for data management and co-simulation. At the end, then, we have validated let's say the standardized simulation toolchain on the workflow with using for industrial relevant use cases. So this is the basic idea of where we stand from HiFi Elements. I showed this already last year on the ECVIA meeting, so just quickly going through this. We have several phases in the development project, going from a concept phase to detailing phase, and later to mill, ZIL, and hardware in the loop, and finally test bench. And we with let's say state-of-the-art workflow, we have discontinuities in which we cannot really further develop because we are missing, let's say, an overall standard where simulation codes can be then exchanged, and that means that teams cannot really efficiently work together. So we have decided that we want to define this encompassing interface and architectural standard in order to overcome these problems. We are using public standards like FMU, FMI for this, and we are also using tools like co-simulation in order to do so. So by means of this, we already have, let's say, fulfilled our first objective by defining architectural simulation standards and its physical partition. So usually when you do such a BEV simulation or a mill and hill and use simulation tools, for example, each of the simulation tools, which might be commercial, like Cooley, GT Drive, or whatever, they are looking at a specific, let's say, physical discipline, either the thermal discipline like Cooley, or let's say the mechanical or electrical discipline. But that would be across the components. So that means that the simulation tool would then take care of, in the, let's say, state-of-the-art approach, take care of many components at the same time. And one of the components is always, let's say, represented by different simulation tools. Here in HiFi Elements, we want to improve exchangeability. And therefore, we have said we put together the component into one model and put also the controls to it. And that would cover all the physical disciplines, which means that we have to have co-simulation. For example, that a simulation tool like Cooley has to exchange the information with some kind of FMU or MATLAB Simulink that takes care of the thermal system within the e-machine or the battery, etc. So here, the other two vehicles that we have taken care of. This is, let's say here, this van and this light duty transporter, the Fiat Doblo electric and the Iveco Daily electric. Furthermore, we have then recommended standards, which is the standard is the electric modeling architecture. It has been publicly made available. It's a public proposal standard for the component model interface, and it was developed systematically using systems engineering-based methods. It supports, as I said before, co-simulation, X in the loop test, and public standards in FMI, FMU. It covers a number of different vehicle architectures that you can see here. Our simulation tool chain and data management performs the management, the validation, integration, and the simulation of component models. It also validates once you put in like in a basket, a shopping cart situation, the different component models. It validates if these work together. It includes a tool for the automatic generation of test cases and oracles for simulation models. That means we can execute quite a number of tests automatically by means of a domain-specific language, which then formulates the requirements to fulfill these tests. We also are able to calibrate model parameters against a certain physical behavior. So for example, you have a component and you have a model which needs to be parameterized to behave, to mimic this behavior of the physical component. Our simulation toolchain also can do so. We're using tools here like XMod from FEV, DSpace, Connect. We're using SysML. We support, as I said, FMI, FMU. Coolie was used. We can use with C codes. We can in MATLAB Simulink can be used. And so this basically is our tool chain. In another objective, we have looked at this from the modeling perspective. So we have developed lots of component models, and at the end, we have shown in use cases, for example, this e-motor and the use case, that we can execute a mill-to-hill use case in order to run this in a test bench in a transient way as it was in the simulated vehicle. So the e-machine and the inverter of the e-machine, they are physically represented, and otherwise everything else on this test bench is just a virtual vehicle represented by a battery emulator, by a dyno, which simulates the resistance of this, and everything else, the whole vehicle and the other components, they are all included in a vehicle simulator, so on the mill. And we have evaluated this also to see how we can optimize our workflow using these results. Here I will show this later. Second objective for this mill to hill was battery in the loop testing. It shows you the testing of a battery in early stages of the development in a controlled environment with high repeatability. Also here the battery hill was formulated, and it was coupled then with a, let's say, realistic vehicle model using a hill and the co-simulation. And the other objective was to look at exemplary reduction of energy consumption by concept simulation. So this is just an, let's say, exemplary result, for what we found out. It's maybe not transferable to real world in all cases, so it could be different. We have seen that we can by means of our simulation then define an optimal hardware architecture, or also, let's say, speed advice optimization, so something like which goes in the topic of controls by up to 18%. So up to 8% energy can be consumption can be reduced by just reducing the hardware demand. So we can look at different hardware components much easier and do the simulation in the concept phase and find the optimal way. And since we have the BOHIFI elements development, we can do so much more and much easier. So look at different candidates of components and also then fine tune, let's say, the whole setup of the battery electric vehicle much better, so that we can come up to a reduction in energy consumption just by means of this, and also by the way that we are able to perform a tool chain enabled holistic speed advice optimization. We gain another energy consumption just by 12%, so that we can reach this objective here nearly. If we look, let's say, at the reduction of powertrain development efforts in total from the concept to the controls, we see that by using all the different ways, we can save up to, let's say, 60 to 70% in efforts. And I think this is a great achievement. Main topic comes from that we have a standardized interface, so we can reuse component models without any, let's say, major efforts. So from previous projects, they could be taken over. We can also exchange with different suppliers component models if they stick to this standard, and then it can be easier used in our simulation environment by means of almost plug and play. We are able to, let's say, execute more tests, because all the tests that we want to define, they are defined by this testing language and then automatically generated. And what I would like to, let's say, give you away with this presentation here. So HiFi achievements is recommendation of standards, the reduction of development and testing efforts by more than 50%, as you saw. So it was even higher than that. We have almost achieved our objective in the decrease of energy vehicle consumptions by up to 20%. And we are able to increase the test coverage with our simulation tools more than up to tenfold, actually. Outlook of what I see beyond HiFi elements is that other research projects already now consider and plan to use the results of HiFi elements, for example, Devolver and Selfie. Nevertheless, what should be done beyond HiFi elements is that this proposed standard should be maintained beyond the end of this project. And of course, let's say the more people work on this, if we have more hands-on experience with the standards that have been developed, it would definitely improve the set of the functional requirements for component model developments, and it could be then spread further towards the community. And of course, we have looked at battery electric vehicles only, but Outlook could be also to include further technology packages like fuel cell and hybrid. So this is it. If you would like to visit us, our results, they are most of them publicly available. Visit our website, www.hifi-elements.eu.